Elon Musk once said that humanity might exist solely to create silicon-based digital life. In today's video, we're going to talk about other possible forms of life in the universe, their strengths and weaknesses. As the saying goes, know yourself and know your enemy, and you will never be defeated in 100 battles. If you don't watch this video, one day your household robot might take you out, and you won't even know why. First of all, there are two possible forms of silicon-based life. The first is directly replacing the carbon atoms in the human body with silicon atoms. Comparing silicon and carbon, they're in the same group of elements, both with 4 electrons in their outermost shell. Carbon has 2, 4, and silicon has 2, 8, 4. Since the outer electron count is the same, they share many properties and can form similar compounds. For example, the most common carbon-based organic substances are oils: gasoline, kerosene, diesel, fish oil, olive oil, peanut oil, etc. Silicon can also form silicones, cosmetic oils, silicone greases, lubricants. If you rub them on, don't they basically serve the same purpose? The reason we are called carbon-based life is that carbon forms the backbone of the large molecules in our bodies. Take this molecule, for example. The entire skeleton is made of carbon. Scientists have discovered that sulfur, boron, and silicon could also serve as alternative structural elements. But here's the issue. Sulfur-based polymers form only linear chains, which limits biodiversity. Boron has the opposite problem. It forms overly complex clusters. That leaves silicon. And when you compare silicon compounds to carbon-based ones, they look surprisingly similar. That's why silicon-based life is currently considered the most plausible alternative. Silicon has another advantage. It's the second most abundant element on Earth, making up 28% of the crust, second only to oxygen. Carbon, on the other hand, makes up only 0.02%. A quick calculation shows that if life were silicon-based, the biomass on Earth could be 1,400 times greater. That's like playing Age of Empires and having your population cap jump from 200 to 280,000. You'd strip mine all the gold and fight endless wars. But then people ask, if silicon is so great, why is carbon life ruling the Earth instead? Well, silicon-based life has its flaws. Complex macromolecules resembling proteins made with silicon are extremely sensitive. They cannot coexist with oxygen. Carbon-based organisms like us love water, but for silicon-based beings, water, an oxygen-rich compound, is deadly poison. Contact with it would trigger a reaction that turns them into silicon dioxide, i.e., sand. That's like throwing a carbon-based human into a vat of sulfuric acid. Your water, proteins, and fats would all react violently. But flip it around, silicon beings could happily bathe in sulfuric acid. For them, H2SO4 would be just water. Remember the Alien movies? The xenomorphs were designed as silicon-based life, which is why their blood is strong acid that burns through us carbon-based creatures. Pretty scientifically accurate, actually. Another drawback: when we carbon-based beings exhale, we release CO2 gas. A silicon-based being would excrete solid silicon dioxide instead. An adult human exhales about 1 kilogram of CO2 daily. Converted into silicon dioxide, that would be about 1.5 kilograms of sand every day. So yes, silicon beings would basically be pooping sand daily. Maybe their anuses are rock solid too. Unless Earth's global temperature rose to around 2,230 degrees Celsius, in which case silicon dioxide would become gaseous. Then silicon-based life could actually breathe through nostrils like us. So far, I've been imagining silicon life in carbon-like terms, which requires Earth to be pretty hot. But what if Earth got colder instead? At very low temperatures, something strange happens: superconductivity. Electrical resistance vanishes and current can flow forever without dissipation. Could current itself count as life? Yes, it could. That's the second form of silicon-based life, not relying on complex compounds at all, but instead using silicon mixed with rare earth elements to sustain current flows. In other words, advanced computer chips, cyberpunk mechanical ascension. That's the kind of silicon life Musk was talking about. Okay, now let's get into the real deal. The three most extreme forms of life imagined in the universe. There's a science fiction novel called Dragon's Egg, which describes a life form called Chila that lives on a neutron star. Since neutron stars have gravity 67 trillion times stronger than Earth's, Chila can't be large. They're only about 0.5 millimeters thick and 5 millimeters wide. The neutron star is basically a smooth iron sphere with no scenery, so Chila's 0.1 millimeter eyes can only perceive the X-rays emitted by the star. Because the star spins so fast, one rotation every 0.2 seconds, evolution happens at lightning speed. Chila's entire lifespan is only 40 minutes, equivalent to a human dying at age 32. What's the advantage? According to the novel, when ancient Egyptians were building pyramids, Chila life had just appeared. By May 22, 2050, they had agriculture, and by June of the same year, their technology was far ahead of humanity's. The logic: short lifespans can actually accelerate innovation. Humans, by prolonging lifespan, may be limiting progress. Think about it. People in middle age really do lose imagination, vitality, and hormonal drive. Many great inventions were made before scientists hit 40, Einstein's relativity at 26, Bell's telephone at 29, Newton's gravity at 24, Darwin's natural selection at 29, Turing's machine at 26. But the novel's most brilliant idea isn't that. It's that under such intense gravity, Chila couldn't be made of atoms bonded by electrons. Instead, their bodies are held together by the strongest force in the universe, the strong nuclear force. Quarks bound by gluons form their structure. In other words, Chila are quark-based life forms. Who said life must depend on chemistry or on atoms at all? Next, let's ask, what is life? If something contains information that resists assimilation by its environment, can replicate itself, and actively adapts, it can be considered life. It doesn't need to be tied to a physical body. For humans, life's essence is DNA replication. Our brains are just tools. So, if we can find any structure in the universe that encodes information and replicates faster than it decays, that could count as life. An international research team from the Russian Academy of Sciences, the Max Planck Institute, and the University of Sydney followed this logic to search for inorganic life in the cosmos. They looked at plasma, the fourth state of matter beyond solid, liquid, and gas. You might think plasma is rare, but in fact, 99% of the universe is plasma. Stars are giant balls of it. They discovered that in microgravity, charged dust particles within plasma can self-organize into stable double helix structures. Even more astonishing, these structures showed thermodynamic and evolutionary behaviors we once thought exclusive to living matter. They could attract more interstellar dust to grow and even self-replicate into two helices. It gets crazier. In 2006, astronomers using the Spitzer Space Telescope discovered a bizarre nebula 300 light-years from the Milky Way's central black hole. It was shaped like a massive double helix, 80 light-years long, 25 wide, made of entwined cosmic dust strands. Japanese scientists later suggested it was material ejected by the black hole, twisted by intense magnetic fields. Whose double helix is that? Could it be the genetic code of a creator civilization? And just when you think this is the peak of mind-bending ideas, here comes the final one. In 2022, Physics Letters published a paper proposing a kind of cosmic string life. Note, not string theory strings, but actual cosmic strings. So what are cosmic strings? Right after the Big Bang, space wasn't smooth. It was like a carpet with all the fibers standing up. As the universe cooled, fibers started falling in random directions. If two areas bent toward each other, the meeting line left behind was a cosmic string. Scientists believe our universe still contains many such defects. This leads to the concept of magnetic monopoles, particles with only a north or south magnetic pole. Under stellar gravity, cosmic strings can thread these monopoles together like beads on a string. Then something incredible happens. The monopoles split into paired half-poles, essentially forming a DNA analog. Just like DNA uses AT and GC base pairs, these half-poles naturally pair into two sets. The resulting structure looks almost identical to a double helix. Even better, stellar energy helps these cosmic DNA strands replicate while also destroying unstable versions. The survivors persist. That's natural selection. If this idea holds, it would be the most bizarre form of life in the universe, life made of space itself. Such beings would be nurtured by stellar energy, their mother stars feeding them with chaotic high-temperature particles. Purely spatial and energetic life, beyond human comprehension. And yet at their core, their fundamental principle would be the same as ours: replication, evolution, selection. Perhaps that is the most astonishing truth of all.